This slide is about probabilistic PCA, probabilistic principal component analysis, or PPCA. So far, we know PCA, right? So PCA is a linear projection of the data X onto a lower dimensional space Z. And the projection mapping consists of the eigenvectors of the covariance matrix. This is how we know PCA, right? And this PCA can be reformulated as a probabilistic model. And then this probabilistic model can be solved based on the maximum likelihood. Okay, so if we understand the PCA as probabilistic model, then we can make a probabilistic PCA. Probabilistic PCA is a probabilistic version of PCA, but it's slightly different from PCA. But when we assume something, then it can be a PCA, traditional standard PCA. Okay, PPCA is a probabilistic model of PCA for the observed data, and the principal axis can be obtained by a maximum likelihood estimate. Okay, we are going to see this later. And PPCA is actually a generative model. So PCA goes from X to the component, right? But in PPCA, it goes from Z to X. Okay, so the observation X can be obtained by a sampling X conditioned on the latent value Z. So Z is given, okay, the latent variable Z is given, then X can be generated based on Z. Okay, so the direction is different. So in PCA, X is given, then we want to find the dominant component Z. Okay, and if we formulate PCA as a probabilistic model, then there are a couple of advantages. Okay, first one, we can use EM algorithms. Yes, this is an advantage. Okay, so when we use EM algorithm, then we don't need to evaluate the covariance matrix when a few eigenvectors are needed. When we use eigendecomposition, then we have to calculate the covariance matrix first, even when we need just a few eigenvectors. We need to make covariance matrix. Or even when we have a probabilistic PCA, if we solve this PPCA with just simply a maximum likelihood estimate in a closed form, then we have to calculate the covariance. But when we use EM algorithm, then we don't have to. So we're going to see that later. And we can deal with the missing values in the data because we use a probability. Then we can actually model many different cases. And since we have a probabilistic model, then this PCA can be used in other probabilistic models smoothly. Okay, so let's see the formulation of PPCA. So basically, PPCA uses Gaussian distributions, and we have Z. Z is an explicit latent variable with prior distributions, like this. And we have noise with isotropic Gaussian variance, and we have mean and observation. So basically, we have equation like this. So Z is given, okay, then with W and mu and epsilon, we can generate X. Okay, don't get me wrong, X is given. Okay, so X is observation, but in this model, we assume that Z is given and X is generated by these formulations. Okay, so we want to find Z. In this formulation again, Z is given. Okay, then we can generate X. But in practice, X is given, so we want to find W, Z, mu, epsilon, everything. So in generative view, Z is a random variable and the Z is given, or here. Then, based on this equation, we can generate one x here, somewhere around here. So if we have some samples like this, then this sample this sample can be generated by these equations. In that case, z should be around here, okay, and then with epsilon we can generate this one. So all these observed data samples are generated by these equations, okay. But again, in this model, z is given, and based on this g, then all these data samples are generated, okay. So this is that's the contours for the marginal distribution P of x. Now we have a formulation of PPCA, and then we want to estimate the parameters W, mu, and sigma square. Okay, then we can define this marginal distribution, which is likelihood. Okay, so given this mu and W and sigma square, then the probability of the sample can be defined in this way. This equation is coming from this fact, and when we calculate the expectation of x is simply a mu, because W is given and mu is given and epsilon is sigma square is given, then expectation of WZ is actually W times expectation of Z, which is 0, so we can ignore this one, and expectation of mu is mu, and expectation of epsilon is 0, so it's mu. Likewise, if we calculate the covariance of x, then simply we can get this. Okay, so that's why we have mu here and covariance matrix here. Okay, and actually this one is integral of these two product. So now we have equation of likelihood. Then next step is to use maximum likelihood estimate. Okay, so as we did with the single Gaussian distribution, then simply we can take a derivative of a probability of x, then set it to 0. So by that we can get mu, simple. Also, W and sigma square can be obtained in a closed form. Okay, so we're going to talk about this closed form solution later, or we can get this W or sigma square by EM algorithms. Okay, so we're going to talk about it too. And now we have the formulation and we estimated all the parameters. Then by the base rules, then the posterior is actually a mapping from x to z, and the posterior can be obtained by this. Okay, so this is a little tricky, so see the equation 2.1.16 in page 19.3 in Bishop's book, then you can simply get these equations. Okay, we already have P of x and P of x given z. Then now by the base rule, then we can get this one. Okay, so let's assume that we already have this one. Then as the sigma square approaches 0, then the probability of z given x has a mean and the covariance. Then sigma square is 0. It means given x, z will be this one, right? This one is Gaussian distributions. When sigma square approaches 0, then the z given x will be the mean. Okay, think about this Gaussian distribution. Sigma square is 0, then this one will be like this. Okay, then given x, then z will be here, is fixed. This one is the same as the solution from this. And this one is actually the solution from the regression. So we're going to talk about that in the regression chapter. Okay. So in the previous slide, we talked about maximum likelihood estimate for the mean, okay, a mu. And we have a mu, which is simply the sample average. And now we're interested in W and sigma square. Okay, so these two parameters can be estimated based on maximum likelihood estimate. But it's not as simple. So we have log likelihood like this. Okay, this is not complicated. So far, so good. We have to take a derivative with respect to W and with respect to sigma square. But the derivation might be a little complex, so we are not going to go through this derivation, but if you're interested, then you can check this paper. The idea is simple. So we have the equation and take a derivative with respect to W and the sigma square and set them to zeros, then you can get these two equations. Okay, good. Perfect. So we have a PPCA and we can estimate the mu and the W and sigma squares based on maximum likelihood estimate. Perfect. But we can estimate W and sigma square based on the EM algorithms. And why do we need EM algorithm? Because we can use maximum likelihood estimate to estimate all these parameters. So there are a couple of benefits. Okay, then we'll see that at the end of this algorithm. Okay, so we are going to use EM algorithm with missing values z, and z is actually a continuous latent variable. And given this equation, p of x given z and p of z, then let's assume that z is given. Okay, so do you remember in the k-means algorithm or mix-up Gaussian, then we actually assume that we know which component the data sample belongs to. Then we update it. And then after updating, then we reassigned and we updated. And we iteratively did that. So now, for now, let's assume that z is given. Okay. Then the complete data log likelihood is like this. Okay, so this is our likelihood. And then in the E step, we have to calculate the expectation of this log likelihood with fixed W and the sigma square. We are updating W and the sigma square. We have to estimate, but at this step, let's assume that these are fixed. Okay, I'm not gonna go through this derivation, but it's not that complicated. Okay, the derivation might be a little tricky with some index, but if you pay attention carefully, then you can do that. You can make it. Okay, and in these expectations, we have z sub I and g sub I transpose, expectation of this one and expectation of g sub I. Okay, and x is given, and we already estimated this mu based on the sample average, okay, which is maximum likelihood estimate. And W is fixed and sigma is fixed. So we have to estimate, we have to calculate this one and this one. Okay, and this one can be obtained by this one and this one by this one. Okay. And then now in the M step, we have to maximize this expectation with respect to W and sigma squares. Again, in the E step, W and sigma square were kind of fixed. And now we have to update W and sigma square and take a derivative and set them to zeros, then we can get this. So in these equations, if you check these equations, there's no covariance matrix. Okay, that is the beauty of these EM algorithms. Even when the maximum likelihood estimate is possible, okay, but still if we use EM algorithm, then we don't have to calculate the covariance matrix. That is one of advantage of EM algorithms. So EM algorithms repeat equation 1 and 2 until convergence. And if you're interested in for a more efficient implementation, then check. And the next algorithm is factor analysis, which is quite similar to PCA. And also at the same time, factor analysis is quite similar to PPCA. So some people get confused with the difference between factor analysis and PCA. So we'll see what is the difference. So in this slide, we're going to compare this factor analysis to PPCA. Okay. So factor analysis is a linear Gaussian latent variable model where observation has a linear relationship with latent variable as follows, like this. And this equation is exactly the same as PPCA. Okay. And the conditional probability of x given z is defined by this. And for your information, in PPCA, this conditional probability was defined by this. So there is the difference here, psi and sigma square identity matrix. That's the only difference. Other than that, factor analysis is exactly the same as PPCA. Okay, and x is observation, and this is probability of x. And we have a latent variable, and this is the same as PPCA's latent variable, and mean is just the mean, and epsilon is an error, and epsilon has a covariance, diagonal covariance matrix. Okay, so in PPCA, the probability of epsilon is Gaussian with zero mean, and the variance is sigma square times I. But in the factor analysis, we have diagonal matrix, which means all the dimensions are kind of uncorrelated or independent, if you will, but they have different variance. Okay, so something like this. In these dimensions, we have a high variance, but in this dimension, we have a small variance. But this one and this one are uncorrelated. Okay. So we have a covariance and variance. Covariance can be captured by W or Z, and the variance can be captured by epsilon. Okay, Z explains the correlations between the elements of X. Okay, and then epsilon sub I represent variance unique to a particular X sub I. And to be equal to PPCA, the error should be isotropic. So in a sense, factor analysis is more general than PPCA. And since we have more parameters and it is modeling more general case, so factor analysis cannot have a closed form solution. So we have only one option, EM algorithms. Okay. And if we compare PCA and FA, then basically they are doing kind of the same things, but they have different kind of interpretation. And PCA transforms the observations to a new space with a large variance. That's what PCA does. And FA describes observations in terms of latent variable factors. So if you apply PCA and FA, pretty much we will get a similar result, but the interpretation will be different. And in FA, factor analysis, we used just Gaussian distribution, but if we model the FA with a non-Gaussian distribution, then we can go to ICA. So we're going to talk about ICA later.